Welcome back to today's episode where we will take a look at how to extend our small window that we created in one of the previous videos in such a way that we can actually display content that has been drawn with OpenGL. And yes, I'm well aware that OpenGL has been superseded by Vulkan in recent years, and we will also cover that in one of the future videos. But I still think that in order to understand Vulkan properly, you first want to get an idea where we are actually coming from. And this is why we will jump right into the code and take a look at how to create OpenGL content. We already had a previous version of the code, and again I'm going to share this on GitHub, where we created a small window that was basically showing nothing. But this time we will expand on this previous code to display again an empty window, but this time it will come from OpenGL. So let's get started. If you've not watched the previous video on how to create a Win32 window, then I will link it here into this YouTube video and you can take a look first and then continue from this point. But assume you already know how to create a window, then you will be familiar with functions like the WinMain and also the window procedure. This time, let's first take a look at what we changed in our Windows main function. So the important additions in comparison to the last state of the code were that when we register our window class, we want to use as a style the class style OwnDC. DC is device context. I already mentioned that in the last video, but this time it is really going to be important because every window should have its own DC so that we can, for every window, do our own rendering in its own device context. What I've also changed is the extra amount of memory that Windows will allocate when the windows are created. This is why you will now see in the code that for the CB window extra, there is been allocation for the size of an HDC and the size of an HGLRC. HDC, again, device context. GLRC, as you can already imagine, is OpenGL rendering context. And because it has a prefix of H, this is just another window handle, so the size of 2 pointers that we are allocating here. Because for every window, we want to store a reference to the device context as well as to the rendering context. Again, we also want to take a look at this part of the code where we do the message loop. Last time we discussed that we can either use getMessage or peekMessage to implement the message loop, and that for an application that continuously renders something to the screen, a variant of the message loop using peekMessage is much more applicable, because then, while the user is not giving input, we can still update the screen to prevent artifacts in the first place. But later on, we will also see that in that part where the user is not providing input, we still want to update the state of our application. And here we will find a new function called SwapBuffers. And that we have to explain to more detail. So join me in this PowerPoint presentation. What we need to understand is that in order to have smooth rendering, we want to make use of two buffers, indicated here on this slide as the front buffer and the back buffer. What you want to understand is that those two buffers are existing at the same point in time in our device. But while one buffer is currently displayed on the screen, the other buffer is drawn to. And then when the drawing finished, we can swap the two buffers so that the buffer that was previously the buffer that was drawn to becomes the display buffer, and the other one is drawn to. And this is also depicted here in this slide over time. So you see the first frame where the front buffer is the display buffer and the back buffer is the draw buffer. And then when we do the swap buffers, we exchange the two buffers. So in frame 2, the display is from the back buffer and the drawing happens to the front buffer. And then another step further, another call to swap buffers. Again, we change the purpose of these two buffers. And that is exactly what's happening when we call the SwapBuffers in our message loop. But what you can imagine is that maybe our drawing is very simple, so the drawing can happen very quick. Then, when we come to the point in our code where the SwapBuffers is called, of course the content is already in the buffer, so completely drawn, and we can immediately swap those two buffers. But you can also imagine that there is slower hardware where the drawing takes actually longer than the time that passes between two calls of SwapBuffers. Then SwapBuffers is blocking until the draw buffer becomes available and can be turned into the display buffer. Let's now also explore another part of the code where we use the HDC. You remember in the last tutorial we were also taking a look at the createWindowX function, and there was one argument given as the last parameter, which is the param. And here we pass in a reference to our HDC, because during the creation of our window we also want to create the device context that we later on use for the SwapBuffers. Also notice that in terms of ownership, so who is going to get the buffer and who is going to release the buffer, we fall back to a concept of ownership where the ownership is with the window itself. So even though we call the SwapBuffers in our message loop, the main function where the SwapBuffers happens is not the owner of the device context itself, but the window is, as I will show in a minute. That way we can finally control when the device context is actually alive and when it is destroyed. So let's take a look at how this device context is created in the first place, and therefore we want to take a look at the window procedure that, in comparison to last time, we changed quite a bit. So first of all, we now handle also the create message as well as the destroy message. Last time we only handled the close message. And as you can imagine, create and destroy window messages, they act in pairs. So a window that is created eventually is also destroyed. So for a window that receives the create event, if the creation is successful, you also receive the destroy event. If the creation is not successful, then you never receive the destroy event. Similarly to how constructors and destructors in C++ work, a successful invocation to the constructor also eventually invokes the destructor, but if the construction fails, the destructor is also not called. So we also link these two together to do the resource management, especially of the device context, but also of the GL rendering context. And therefore, again, we need to allocate some memory and to store those. And this is done for us because in the window class, we already reserved some extra memory to store the references to the device context as well as the OpenGL rendering context. So let's go through this now step by step. First of all, last time we also discussed about this L result that is returned from the window procedure. And this time we see actually a case where the value that you should return from your window procedure is not null. And that is the case if you want to indicate to the Windows operating system that your creation of the window actually failed. In that case, you just want to return -0 for this L result. So we initialize the L result with -1, and then we go and we get the device context for that window. And if that succeeds, and if we can set a pixel format, I will explain that in a bit, then we go on and then we create from that device context also rendering context. And again, you see the same style of error handling, that is C-style error handling instead of C++ error handling. Then, in order to make use of the rendering context, we want to make it current. You will see in OpenGL that there are specific functions of the family with WGL as a prefix. Those are the Windows functions of OpenGL that you need to call in order to access the OpenGL functionality at all before you can even make proper OpenGL API calls. And the make current function sets the GL rendering context as the current context for the device context, and then within that rendering context we can actually do our drawing. So now we have created a device context, we have created a rendering context, we have made the rendering context current, and then we also want to store references to those two contexts with our window, so that later on in our deletion process we can also properly access them again and destroy them or delete them. And therefore we call a set of functions which is called SetWindowLongPtr, which basically gives us indirect access to this window extra memory so that we can store the data in there. And we need to be a little bit careful because we don't get access to this memory directly, but we can access this by the size of long pointers, so in blocks of long pointers. In this case this can work because the device context as well as the OpenGL rendering context are of exactly the same size. And then we access into this memory from the starting address, so this is where we pass the 0 here, and then later on we, behind the device context, inject our rendering context. And this SetWindowLongPtr has a little bit a strange protocol. So if it returns the 0, then you still do not know if it was successful or not, because it basically returns the previous value that was stored at the memory location. So if that value is 0, which is initially the case, then you still have to call GetLastError afterwards to check if it was successful or not. And this is exactly what is happening here in the code twice. But the SetWindowLongPtr does not reset the last error by itself. This is why before that we have to call SetLastError ourselves, and then we set it to success. And if after the call we still have success in that state, then the call was successful. And then in the very end, using this cast to the create struct in the L param, we return the HDC, so that the party that called create window X in the first place and passed the reference to the HDC gets the HDC in return. And then by setting the LRES to 0, we indicate to Windows that it now may proceed with the creation of the window. And you can also see that for our error handling we used again the goto statements. In this case we even jump over to what is happening in the destroy branch. That way we can prevent that we have duplicate code for our destruction case. You also see that this also nicely plays with this L result, because basically the L result was already -1, and in the destroy we don't modify it at all. So for a normal call to the destroy we will still be 0, and for a call for create where the creation should fail we are -1. And in here we get the references to our device context and the rendering context again from the window extra memory, but only in the case when we are really in the destruction event. If we came from one of the error cases from the create event, then we just release the current rendering context, we destroy it, and we also release the DC. That call ReleaseDC is not actually needed, because Windows has the notion of different kinds of DCs, like private DCs or class DCs, and for the DC that we have at hand we don't need to call the ReleaseDC explicitly, but I still think in order to have matching pairs of acquire and release we should also have a release in here. Now you see that when we went through the creation process of the window that we called two functions, SetPixelFormat and CreateContext, that you might already have spotted at the beginning of the file, because these are functions that we defined ourselves. And those I also want to quickly touch. First of all, let's take a look at the CreateContext function, because that is simple to understand. Again, here we have a WGL function which is exactly having the same name, CreateContext, which creates us a rendering context from a device context. That can only be called if we already set a pixel format for the device context. Basically, we can also ask why are we having this function in the first place, because what we are doing here is we just call the wglCreateContext in it, so there's no added value to this function, and yes, you are right. But in later tutorials, we will explain why this is a smart way to do this, because then we will create more logic in the create context itself. Because, spoiler, what we are doing here is we start an OpenGL window using a very old way of starting an OpenGL window, which I will explain in another video. But in order to prepare already for this next step, where we will create a more up-to-date OpenGL window, this is why we have this create context function on top of the wglCreateContext. Now let's also take a look at the pixel format. Basically, what you want to understand is that for every device context we can set a pixel format which describes the capabilities that a frame buffer should have that is living behind this device context. Basically what we say here is, give us some kind of frame buffer, for example a graphics card or a CPU which has also rendering capabilities, that can fulfill certain requirements. And especially for those requirements, we want to have a frame buffer that can support OpenGL, because that is our intention in the first place, to draw via OpenGL. But we also want to have a frame buffer that can draw to a window, and this is also what you see in here. And we want to have a frame buffer that can do double buffering, as I explained previously, where we have a front buffer and a back buffer, and we draw to different parts of the screen, to different parts of the frame buffer, and then we swap the frame buffers into place. Then of course we want to do some RGBA or RGB based drawing, so no index drawing. We will want to have a full color palette. And then as you can see, many of the members of this struct are set to 0 because they have no meaning in the calls to come. But the important parameters that we want to set is the color bits. This is the number of bits that we get for our R, G, and B. And we want to set the number of alpha bits, which gives us the number of bits for our alpha channel. And then we can also have, here it is called accum bits, but this is basically another buffer that we can make use of to accumulate. This is where the name is coming from. So there we can also give a number of bits. And then we have a depth buffer. If we want to do 3D rendering, it also makes sense to have a depth buffer, because in the depth buffer we can store the information which pixel is sitting behind another pixel. So then we prevent that pixels that are further away from the viewer are drawn on the screen, and only the ones that are closest to the user or closest to the viewer will be coming on active on the screen. And then we have a stencil buffer. This is something like masking. In this eye layer type, we put to main plane. You can also have like different planes where you draw to, but in our case we will always have a main plane where we draw to. And then we call ChoosePixelFormat, which basically takes this pixel format descriptor and looks up all the available pixel formats and tries to find the one that closest matches our pixel format description input. So you can imagine that, for example, we request a pixel format descriptor, a pixel format with a pixel format descriptor where we say we want to have 24 color bits, but then the closest match that we get is maybe 32. That we don't know up front. So this ChoosePixelFormat will give us some pixel format that is close enough to our pixel format descriptor. And the way this is indicated is by passing back a value that is non-zero. And then eventually we also want to call the SetPixelFormat on our device context if we got back a valid format. And we can also take a look at the defaults that we're using here. So basically we want to use 8 bits for every color channel. So this is where we come up with 24 bits. And then for the alpha we also use 8 bits. That is more or less common. For the accumulation buffer, I also choose the 24 bits to match the color bits. And then for the depth buffer, yeah, 16 bits. It depends a little bit on the depth, how many bits you have, how accurate your depth buffer is. So the more you have, the more accurate it is. If you have elements that are very close to each other and you have not enough bits, then you might see flickering on the screen where sometimes a pixel is considered in front, sometimes a pixel is considered behind. So there you have some flexibility to play. And then for the stencil bits, as I said, the masking, we just put 8 here, but it's not important at the moment. So let's take a look now what is going to happen when we run this application. And again, we have created an empty window, but this time it is black, because that is the content of the front buffer and the back buffer that is displayed on the screen. And because we call SwapBuffers eventually, every once in a while, basically it is already swapping, but the content of both buffers is always black, so we don't see that difference. But it is happening in the background. In the next video, we want to expand this further, so we want to create an OpenGL context which can give us access to the latest functionality of OpenGL. And from that point onwards, we go away from OpenGL and we move on with the Vulkan API, because that is the latest way of programming graphics in the first place. But in order to understand the complexity of Vulkan, especially in the initialization part, it is worth to also take a look at OpenGL, which was the older API, to understand what were the limitations, so that we can see why certain steps were taken in Vulkan to improve on the existing functionality in OpenGL. Happy coding, guys!